Okay, so in this lecture we're gonna make a brief recap of radial quantization that we discussed last lecture. And from radial quantization, we will go to operator state correspondence. That is that is the main result of CFTs, at least to my understanding. And we'll discuss operator state correspondence because we want to eventually get to the operator product expansion. But before, we just make a small parenthesis to discuss unitarity bounds. It's just a quick computation. Okay? That has to do with something that I promised you since lecture 2, that if we impose a unitarity constraint on our CFT, then we get some constraints on the spectrum of allowed scaling dimensions. Okay? And just as part of the recap, written here is 3 steps here. What do we actually want to do? Okay, I don't know if you remember, but when we computed the 3-point functions of scalars, say x1, x2, x3, we had this thing here we call the structure constants. Here we had just power loss, okay? And we saw that we can, the computation of the 3-point function fixes us the functional form, namely this power law behavior, where the scale dimensions of these fields appear here, but it does not fix the structure constant, okay? And I will the IJK. Okay? And this is something we do not know by conformal symmetry alone. Okay? By kinematic arguments, we cannot determine this, the structure constant. And similarly for the 4-point function, we had I, xi, blah, blah, blah. And we had similarly some power law behavior here, but instead of a structure constant, we had another function of these 2 variables u and v, which are the conformal invariants. Okay, so conformal symmetry alone fixed the 2-point functions completely, functional form and the constant we fixed by normalization. But fixing the 2-point functions normalization, we cannot fix the structure constant of the 3-point function. And when we get to the 4-point function, the situation is even worse. We still have a functional form that we cannot determine by conformal symmetry alone. Okay, and the goal is exactly to determine the structure constantCijk and the conformal block. This function is known as conformal block. To do this, we need dynamic information. Okay, so it will depend on the specific CFT we are discussing, but the tool to actually do this, to determine the structure constant, the conformal block, is what we know as the operator product expansion, which is a tool for any quantum field theory, even without conformal symmetry, but it really comes into its own when we also have conformal symmetry, okay? Because it becomes much stronger, okay? But in order to arrive at the operator product expansion, we must discuss this so-called operator state correspondence, which is at the heart of CFT, and it is what makes the operator product expansion much more powerful in CFTs as compared to ordinary quantum field theories. And the natural setting to discuss the operator state correspondence is the so-called radial quantization that we discussed last lecture and that I'm going to review here. Okay? So is this the goal of this lecture is clear? Okay? So for those who do not weren't present in the last lecture, review what we learned last lecture on radial quantization. And the idea of radial quantization was to... What is radial quantization, to begin with? It is when we, for ordinary quantum field theory, we take time slices. Okay? We take our space-time and we take equal time surfaces. Okay? We time slice the space-time, so we have something like this. Okay? This equal time surface at t. This will be an equal time surface at t plus delta t. Okay? And there is a evolution operator here that is basically given by the Hamiltonian. Okay? Since it's a unitary operator, then the Hilbert space on this slice is the same as the Hilbert space on this slice. Okay? And this is what we do in usual quantum field theory. Okay? And for CFTs, we could do this as well, but there is a better choice, which is we visualize space-time by using spheres. Okay, meaning we fix our origin. Okay, and then we just take spheres. Okay, this is basically this is radial quantization. Now, why is this useful for? And there will be the same things. We will have an evolution operator. Each sphere will have its own Hilbert space. That will be the same as for any other spheres because the evolution operator will be unitary. And the reason this is more useful for CFTs is because we can exploit the lattice structure. Okay? The lattice structure that we had on conformal algebra. Because the evolution operator here will not be given by the scaling. It's supposed to be the delta R. Okay, the radius. Okay. The evolution operator will now be the scaling operator instead of the Hamiltonian. Okay? And by having this guy as the evolution operator taking eigenstates, the eigenstates in ordinary quantum field theory are eigenstates of the Hamiltonian and the momentum in general. Okay? In particular, the Hamiltonian. And in CFT, we have already anticipated that the eigenstates we choose as, to be the eigenstates of the scaling operator. Okay? Something like that. Okay? And since we have a lattice structure for the eigenvalues of the scaling operator, then it will be useful to use it as the evolution operator. Okay. And in order to do this, we slice space-time by using concentric spheres.
I always get confused here because this is not unitary.
I said it was unitary, right? Yeah, because D is not. Yeah, because D is not a Rician. Because it's not bounded. Yeah.
Yeah, it's not.
But you can. Okay, the Wigner theorem says that if you want to implement a symmetry, given space, it should be either unitary or anti-unitary. Maybe that's anti-unitary. No, I agree with you.
No,
okay.
but
I just said it was unitary.
Well, I just want so you want to have unitary that the Hilbert spaces are the same on every constant radial slices.
Yeah.
That's what you need. So probably I don't know, but maybe unitarity is not necessary. It's a sufficient.
Maybe it's not. Or maybe this guy is anti-unitary. I don't remember.
No, wait.
But you're right. Okay, so for those who don't, let me just recap what's going on.
Okay.
Last lecture, when discussing the radial quantization, one of the things that we discussed, we studied the representations of the conformal algebra on fields or operators. For states, we know that we define primary states as those eigenstates of D have an eigenvalue delta such that the action of the special conformal transformations annihilates the state. Okay, this is the definition of a primary. And then we had descendant states. That were simply taking a primary and acting with p mu. Okay, p mu is the lowering operator, and p mu is the raising operator. Okay, p mu if you want the p squared delta, so on. Okay, and we ask what happens to fields and operators. Okay, and the conclusion was if you take this capital phi represents any field, scalar or spin or fermionic or vector field, doesn't matter. What we found was this. First, use just the usual result from Poincaré invariant theory. Sigma mu is just a spinning matrix, and this is just a orthogonal momentum. And then here comes the new stuff from conformal symmetry. The action of the scaling operator on a field, we found it to be this. That is the eigenvalue. And the action of the k mu on a field was found to be just to remind you how we reached this, how we found this result. We looked for representations of these operators for fields located at the origin. We took, we said, okay, M acting on a field located at the origin should be the sum of the spinning. Okay, we cannot have an orbital momentum. We took the scaling and to K2. I said, okay, this will furnish, this will be some operator delta tilde, this is going to be some operator kappa, and if they are indeed representations, then they must close the same algebra, and you use the, if you recall, for the conformal algebra, M and D commute, so if these two guys commute to furnish a representation, then by Schur's lemma, the standard theorem on any algebra representation theory, it states that this guy must be proportional to the identity. So this delta tilde is just a number. Okay? And as a consequence, if you also recall that D commuting with kappa, with k mu, is proportional to k mu. But if D is proportional to the identity, then the commutation is 0. So this kappa must be 0 too. Okay? And then there's a further theorem of representation theory that said that, and this I arrived at the discussion we had that. It says that since the scaling is an unbounded transformation, okay, you can go to infinity. There's not a limit to them. Then there's a theory that says that if we try to give a finite representation to an unbounded transformation, then the operator is not a Hermitian, and the eigenvalues must be pure imaginary. That's why we have this factor of I, namely delta tilde, like I delta. Okay? And come back to the discussion that Tobias started.
But I think, okay, but you, like in the usual case, you want to have that the Hilbert space stays the same.
Yeah.
That's the reason. Now, if you take as a time evolution anyway, the exponential of the operator which defines like your eigenstates, then I mean the eigenstates stay the same. No, you don't need to have a unitary. I don't know if this was clear what I was saying.
Yeah, the eigenstates will be the same.
So you don't need to have a unitary operator, just because you take the exponentiated operator by which you define the eigenstates. No, I mean which gave you a basis. So
let me just D is it's like it's written as minus I delta x dot partial. If we take D dagger, okay, but there's another thing in red we have. You were in this section. Let me see if I have the. I don't. Okay, the point is, dagger in CFTs means a different thing. It is not. Dagger on CFT is different from transpose complex conjugate. Okay? Because why? I don't remember the result, so let's draw this first. From the ladder algebra, we had this. Okay. And in the ladder algebra, we have that the lowering and the raising and the lowering operators are conjugate to each other in some sense. Okay. In the usual quantum mechanics and quantum field theory, this is just the relation. Say for the harmonic oscillator, the annihilation equation operators. One is just the transpose complex conjugate of the other. Okay, the usual Hermitian conjugate. Okay, the usual dagger. And whereas for CFT, well, if you look at this, then it certainly cannot be. Okay, just transposing and taking the complex conjugate. And so, what is this conjugate in CFT? We have to remember that in the second lecture, I guess I told you that special conformal transformation can be understood as an inversion conjugated translation. Okay? We invert, apply an inversion to a space, translate in this reciprocal space, and then invert back. This generates a special conformal transformation. And it is in this sense that these operators are conjugated. Okay, so dagger in CFT. So maybe I'll write over here. I mean, we could probably should have used another symbol, but we just use the dagger. Okay? Dagger in CFT means inversion conjugate. Okay, so we write p mu dagger as p mu and vice versa. Okay? P mu dagger is p mu, where this dagger is just k equals inversion, translation, inversion, and vice versa. Okay? So dagger and CFTs have another meaning. And so to answer this question, maybe you have to treat unitarity and say this Hermitian by using this definition of conjugates. And I haven't done this, I'm not sure of the answer.
But you could, in CFT, you could define the regular Hermitian conjugate.
Yeah, you can define
but it's
it.
not useful. It's not useful.
Yeah, people just, when they usually write dagger and CFT, they mean this.
Okay.
Okay? Because I don't know what point you can center, but the motivation for this definition is just the ladder algebra. Okay? The dp gives p and dk gives minus k. And in a ladder algebra, the lowering and raising operators are conjugate to each other. In usual quantum mechanics and quantum field theory, the conjugate is just the Hermitian conjugate. In CFTs, the conjugate means this. Okay? Because a special conformal transformation is an inversion conjugated transformation and vice versa. Okay? So if you say delta dagger on a CFT, it is just not simply taking this, putting a plus here, reversing this guy, so exposing. You should conjugate it with inversions. And if I remember, I don't know if I commented this on last lecture or if I just presented this result, but an inverse conjugated scaling gives inverse scaling. So if you dilate by 2, then this conjugate will be contracted by half. Okay, this is the fact for scaling. But okay, going back to your question. You're right. I mean that this operates not unitary, and this is not unitary in the usual sense of ordinary quantum field theory. But to treat this problem in the setting of CFTs, we have to go this way. And I'm not sure of the answer. Okay. But surely the evolution operator in this radial quantization is the scaling operator. Okay, you just choose an origin, which is arbitrary, but you have the same arbitrariness as choosing the time slices on the usual quantization. Okay, so you fix an origin and then we evolve everything by applying the scaling operator. Okay, so you slice your space-time by spheres, conceptual spheres, instead of equal time slices. Okay, and again, the reason to do this is to exploit the value structure for the eigenvalues of the scaling operator, which is now your evolution operator as well. Okay.
Is still Hermitian, the D.
In the usual sense? I mean, just transposing
yeah. In the usual sense, is anti-Hermitian because purely imaginary eigenvalues.
Yeah, because this guy is a number. Yeah. So if you look at this piece, you just get a plus here. This guy is just a number. Then yeah. It's in the usual sense of Hermitian conjugation, it is anti-Hermitian.
So the U, since he is anti-Hermitian, the U is anti-unitary.
No, anti-unitary is something else. No. Anti-unitary is
yes.
Gonzaga equals minus identity, right?
No. No, anti-unitary
Or
is anti-linear and preserves the.
Okay, so you want to talk about Wigner's theorem?
Yes.
Implementing symmetry in a Hilbert space. So the theorem is symmetry transformation must be implemented as unitary operators, unitary and linear, or anti-unitary, anti-linear. Yeah.
Yes.
That is different. But I don't know because the stats of this theorem for CFTs if you do radial quantization, because at least the conjugate is the conjugate in this sense.
This is what I thought when I watched this. I didn't came last lecture.
That's why I'm doing the recap.
But I watched the line.
Okay.
Because when you exponentiate a Hermitian operator, you get a unitary operator.
Yeah.
But when you exponentiate anti-Hermitian, you get an anti-unitary.
No, that's unitary something else, but you don't get a unitary operator for sure. Yeah. Or maybe there's different definition of the anti-unitary.
Yeah, okay.
Any more questions, comments? So, what is that to say? Okay, yeah. We were looking at the representations of the conformal algebra on fields. Again, on states we know they fall into primary states and descendant states are organized in this way. And for fields, we found this representation. These are differential operators. And we make the same definition. We say that any field or operator that is annihilated by the special conformal transformation is a primary. Okay? This is defined to be a primary.
Can I, no, maybe. No, I just, because, let me just, if I take the momentum basis, like usually, okay, there can be internal degrees of freedom, but I know that the eigenstates of the momentum operator like form a complete basis or whatever. So do I know something similar for your D, that the eigenstates form like a complete
Oh, they should.
basis? They should, okay.
I mean, they should.
That's it.
Well,
Okay.
I mean, in general, you also have spinning here. Just consider scalars for simplicity. Okay, the eigenstates both here and here.
You can have it.
If the particle has the states have spins, then you have eigenstates of m nu as well. Okay, because remember from the conformal algebra, m nu does commute with the scalars. Okay, so we can make the same definition for fields and operators. If they are annihilated by the special conformal transformation, then they are primary. And there is in general, this is a hardest task to solve this differential equation. Okay, but there is a trivial, in a sense, solution. There is a natural set of primary fields namely those fields that are located at the origin. Because if you rely on the origin, then everything here has x mu or x squared. So this vanishes identically. Or you could have anticipated this by the fact that when we discussed the representation of the origin, then the matrix cap that represented the action of the special conformal transformations just vanishes. Okay? So this is a natural set of primary operators. Okay? In CFT, I will use the fields and operators interchangeably. Okay? This is important remark. When you do standard quantum field theory, when we refer to fields, we mean the fundamental fields that enter the Lagrangian. See? So if I say a scalar field theory, I mean one scalar field. Okay? So I have the mu phi squared plus half m squared phi squared, and I say that I have only one field, phi. Okay, and I have a bunch of operators. Okay, the mu phi as an operator, phi squared as another operator, because fields are operators, of course. And we make this distinction. Okay, I have this keep track of the degrees of freedom and so on. But on CFTs, we use them interchangeably. Okay, when we say a field and operator, we mean the same thing. Okay, so for example, when you compute these correlation functions for these fields, this is valid for any operators. Okay, I could compute the mu phi here, the mu phi here, and compute correlation functions. Okay, in the same way. Okay, it does not mean that the theory are harder because they have more fields. It's just a change of nomenclature. Okay, just calling fields and operators interchangeably. Mainly because the conformal symmetry allows us to do this, to treat them any fundamental field that we want to think of as fundamental field or anything that is derived from it, by taking the rings and so on, more or less on the same footing. Okay. And sometimes then when I will write instead of a field, I'll write an operator like this. Okay. I'll use this interchangeably. And so okay. So we'll come back. We have this natural set of primary fields. These fields located at the origin. And the descendant fields will be just okay. We can simply act mu square, so on. Okay, for these fields. I can also, of course, have a primary field away from the origin, but in principle, I would have to solve that equation, which is hard. And it becomes a bit simple for scalars because these terms will die. Okay? but still kind of annoying. And this is another remark. When I didn't tell you, because I actually forgot. When I compute this correlation function, the 2-point, 3-point, 4-point functions, that game works only for primary fields, okay? Because I also did not show you, but you can define the transformation of a field under conformal transformation, say the field is a function of x. Then you do a conformal transformation, get some Jacobians, and so on. And these Jacobians will have the form of those scaling factors omega. I guess I call them omega on the second lecture. And you can also use this way to derive the correlators, but it will only work for primaries. I mean, you only have these simple forms, simple structure for primaries. The reason is if you have a descendant, you have this additional factor of the mu, and this will give another contribution. Okay, this will give more contributions here. Okay, and since we can only look for primary fields, if we solve for the primary fields, then we can just apply these guys to get everything else. So in CFTs, that's the reason why you only confine our attention to primary fields. Okay, because primary fields are related to primary states, and primary fields have a really simple correlation functions, simple, as simple as it can be for CFTs. And that's it, okay? So, and the fact that I can have a primary field away from the origin is consistent with this fact, okay? If I could not solve this differential equation, then there would be no sense in computing correlation functions here away from the origin, okay? So, moving on. Maybe I should. Okay, are there any questions about this? I'll give. We have questions. So, okay.
Just, I don't understand P0. Isn't it 0? I
mean, yeah. You act mu, then you set that to 0.
Okay.
It's just.
But then you need to know not phi of 0, but you have to know phi in the vicinity of. Okay, so.
Yeah.
When you say fields at the origin, actually when you have phi of 0, then you have the field at the origin is an operator. The field is like is a function that at every point in space it gives you a.
No, I'm looking at the origin.
And now when you take if you take any field and evaluate it in the origin, you get a primary operator.
Yeah, I have a primary field or primary operator by definition. Okay, and the thing that we'll do next, we'll relate these fields here, this natural set of primary fields, to these primary independent states. Okay, that will be the content. This will be the content of the operator state correspondence. Okay.
And since you choose the origin. Is a particular choice.
Yeah, I can choose.
And you constructed that the fields at the origin, they are primary. So isn't that that's a choice?
That's a choice, yeah. But okay, first of all, remember that if we labeling our states by scaling dimension, namely if we're using the scaling operator to organize our Hilbert space, then we cannot measure anymore the momentum, energy and momentum. Okay. So this question, that is one way to think about it. And the second way to think about it is just okay, it's just a choice, but I could do this for any other point. I could choose this guy here, this point here, as the origin, inherit the process. Okay. The computation might change a little bit, but the result will be the same. The physical results, the physical predictions will be the same. We have the same arbitrariness in this time slicing quantization. Okay, we have to fix t equals 0. Okay, if you want to, we have to fix time like vector to guide you to. It's a choice, okay, but it will lead to the same physical predictions. Okay. More questions? No. Okay, so let me just highlight to emphasize one thing that regarding this structure of the states and fields on CFT. It's gonna to be some quick examples, some practice, and getting used to. Since by definition, descendants are found by acting with momentum generator on fields and operators or states, and at least one. Okay, let's focus on the operators. The representation is just a derivative. Okay, so we can think. Okay, take a scalar field. Okay, not like this. I did not put a mass because this guy would probably just spoil. Simulate the conformal symbol. We'll call phi. Okay, let's first just discuss the free theory. Okay, then I'll plug in the interactions. Okay. Okay. Now this has conformal symbol. Phi will be a primary. Okay. Why? How do we know immediately that phi should be a primary? Because phi is not the derivative of any other, say, vector field. Why not? Because there are no vector fields in our field. Okay, you could introduce vector fields and start playing games, but if you don't want to, okay? There are systems in nature that are perfectly well described by scalar fields alone. Okay, and in this case, phi is a primary. Okay, that also means that phi squared or any power of phi will be a primary. Okay, for the same reason. But okay, this is a kinetic operator here. The mu is a descendant. Okay. And say if this is in 2 dimensions, for example, then the phi field has the usual mass dimension will be just 0. Okay. Okay. The equals 2, then the scalar field has mass dimension 0. And since this is a free theory, this will coincide with the scaling dimension. Okay. And then what this means is phi, this guy has 0 mass scaling dimension, this guy has 0 scaling dimension, and so on. This guy will have scaling dimension 1. Okay? Why? Because phi has 0, the mu is just the raising operator, so it increases by 1. Okay? And this, again, since it's a free theory, just coincides to what we usually are used to do by counting mass dimensions. Okay, derivatives have mass dimension 1, and so on. Okay, but the game changes if we have an interacting theory, because first of all, we have infinite primaries here. Okay, so we could see the hopeless, because in a CFT we want to solve the theory. We want to solve this maybe this structure constants and conformal blocks for all primaries. If you do it for all primaries, then we can just apply translation operator, generator, and get the results for the descendants, and then I have all correlation functions of my theory, so I solve my theory completely. Okay? And the free theory just seems okay, alright? If the free theory already has infinite primaries, then you would expect the interactive theory to be more complicated, but it is not true. Okay? If we add now the by 4 interaction here. One thing that happens is the equation of motion. I guess this was also discussed last lecture. Tobias has something about this. The equation of motion is basically this. Okay. Okay. So these are two translation operators, mu squared. So we see that, okay, we have Phi is a primary. Okay. Phi squared is also a primary. But phi to the third power is a descendant. Okay, because of the equation of motion. Okay, so this is what usually happens in interacting conformal field theory. You have way less primaries. Okay, okay, we do also have phi to the fourth.
Any larger power would still be a descendant.
No.
Oh, no.
Descendants are. Here's the thing.
They need to be explicitly.
Descendants are found by applying the transformation operator, not by multiplying the fields over and over again. Okay. So here's where the things start to make to deviate from what we used to in ordinary quantum field theory. Okay. Phi to the fourth, okay, any other power here, k, bigger than 3, would okay, I don't know any, but there will be okay. There will be another primaries here. Okay, there will be more primaries. 2. Okay, but the thing is, if we treating interacting field theory, then we have to first study what is the relevant interactions. Okay, if you're interested in the infrared. Okay. And it turns out that phi to the 4 would be a primary. I don't remember, but I guess phi to the 4, this guy would be a primary, but it is irrelevant. Okay. And so we discard anything else, phi to the 5th, to the 6th, and so on. Okay. So when we study and interacting conformal field theory, we usually if there's a CFT, we have to look for the primaries. Okay. And we'll typically still have infinite primaries, rigorously speaking, but if we have an interacting theory on top of that, then we can also look only to the relevant operators, okay, to the relevant fields. So we look for the primary relevant fields, okay, because the contribution of the others will just go to 0.
Relevant in the sense.
There's the sense of the normalization group. Okay. Just to give you a result, I'm not deriving this. I'm just telling you the result. Okay. If you study the Ising model, yes, the Ising model in 3 dimensions. Okay, the Ising model is actually solvable in 2 dimensions. You have an analytic solution, and in 3 dimensions it was really a challenge. But it turns out that is at the critical point it is a CFT described by this. Okay? And the relevant operators are these guys. Okay? And the result is what's it? I mean, these are the only at least spinless primary relevant fields on the Ising tree at the critical point. Okay? If you want to describe it as a field theory. And the result for the scaling dimensions is, okay, the scaling dimension of phi is something around, it was found to be something around 0.51, okay, which is pretty close to what it would be for the free theory, okay, in 3 dimensions. Okay. If we had these are going in 3 dimensions, then the phi field would have scaling dimension half. Okay, so it's pretty close. But here comes a surprise, so to speak. The phi squared has scaling dimension 1.41. Okay, so if you would apply your intuition for ordinary quantum field theory, even interacting quantum field theory by counting mass dimensions, okay, expressing mass dimensions, then we would think, okay, if phi has mass dimension half, then phi squared has mass dimension 1. This is not true. Okay, this is found to be. Okay, why? It deviates so much because this is an interacting system. In fact, a strongly interacting system. Okay, this is one of the signatures of a strongly interacting problem. Okay, so okay. phi is it's bigger than 1. Okay. It's a strongly interacting problem. And the effect of interactions has this anomalous dimension, if you're using some quantum field theory terminology here. Okay? And this is the result. Okay? It deviates from what we would usually expect from ordinary quantum field theory. And here's the check. If you compute the scaling dimension of phi to the third power was found to be just 2. Would be something just like this. Okay? Which is consistent because it becomes a descent. Okay? And there's 2 powers of momentum here, so we raise the scaling dimension 2 times. So plus this plus 2. Have this. Okay? So it is a bit unusual if you're only used to standard quantum field theory and mass dimension counting. If you're dealing with a CFT or any strongly coupled system, then you have to be careful with this. Okay? In CFT, if the strongly coupled system is also CFT, then at least you have this method to compute these things. Okay? But then the message that it deviates from our expectations. Okay?
Do you know how this was computed?
Okay.
No.
It was computed using the OP.
But then compared with simulations? Or?
And then they do simulations. Probably in CFT is strongly coupled. It's strongly coupled, so you usually have to do simulations. And what you compute numerically is whatever comes out from that OP that we learn about. Okay, it will be just a series. Okay, series expansion. Okay, so I guess that was what I want to talk about. And just as a last remark, of course, we have primary states, primary fields, descendant fields, and generic state or generic field will be just a linear combination of those. Okay, just like in quantum mechanics, you have energy eigenstates, and then a wave function is usually a linear combination of the eigenstates. Okay, so a general state or general field in CFT will be just a linear combination of primaries and descendants. Okay. Okay. So let's now start talking about the operator state correspondence itself. Okay. Any questions about this? Remarks? No? You have questions?
just something stupid. Just if I wasn't like stupid enough to say I want to see like in the calculation that the free theory has like phi as a primary field, I would apply this k to phi and then use the equations of motion, no?
Well, you'd have to. If you want to check that the phi is a primary, then
I should.
You have to solve. We have to. Okay, this becomes your phi. You do this to 0. You have differential equation. This guy dies because
exactly. So I just do it very stupidly. I say, well, equation of motions tell me that the gradient of phi is a constant. Because like the plus in is 0, so delta.
Oh yeah, okay. Because I was looking at this. Yeah.
So if I just plug this into this equation, how can I see that this is true?
Okay, have to solve it.
No, but I mean, let's just say the sigma 0, then I just do for the derivatives, I guess I could just say it's a constant, no? Or do I say something?
Yeah, so phi will have to be some at most linear, something like this.
Exactly.
Right?
So I plug in there, and then I have like, I don't see that
everything
zero.
Everything has one derivative here only.
So these are all constants, but they should somehow cancel each other. So delta is 0, you're saying, no? That's like...
Okay, have this guy, so say if we have... okay, say for simple, we have 2 dimension 2, so this guy is 0.
It's 0, so I have to see that
this goes away because it's spinless.
And I don't see that these cancel. But maybe, but it should be constant, no? It should be linear maybe I'm saying something stupid because it cannot depend on the coordinate, so it has to be something more complicated.
That's something like, okay, this that's something like.
I think I said something wrong. So I think
some concepts.
it's not a constant. I mean, it cannot be. It has to be. It cannot
Yeah,
depend on
yeah,
indices, so probably the derivative already mentions. I don't know, but okay. So
In principle, that's
it should.
and you see why people don't go on solving that.
Yeah.
Okay, just and again, just to emphasize, this is to avoid computing this is one of the reasons why that embedding formula is useful. Okay, because you just translate this problem of conformal symmetry to Lorentz symmetry. Okay, rotation symmetry, and then we just project that and all that. Okay. Any more questions before we move to operator state correspondence? No? Okay. One thing you should have played this game inside correlation functions. These are operator statements.
Okay.
So, for example, one thing you can do is you know this correlation function, okay, by conformal symmetry. Okay, x1, x2, for example. And then if you act with mu here, this action should be consistent with this the form of this correlation function if phi is to be a prime. Okay. These are operator statements. So if you use this to actually compute something in the field theory, you should do inside correlation functions. Okay, not just like by themselves. So maybe that's we can over that. And their action actually has to do with the wide identities that I haven't discussed yet because I still haven't discussed the energy momentum tensor. CFTs. I haven't discussed the conserved currents that come from conformal symmetry and the properties that this implies to the energy momentum tensor, including the wide identities. This will be discussed probably when I finish this in the next lecture or maybe the two next lectures. Okay? Let's go back to making analogies between usual quantum field theory and CFTs. In the usual quantum field theory, we discussed that the eigenstates are momentum eigenstates. I'm not taking spin as states for simplicity. Okay. And the question is, how do these states arise? How do I create states? In the usual quantum field theory, I already know the answer. We act with creation operates on the vacuum. Okay, and here we'll just highlight the relevant properties of this process for comparing it to what we were doing in CFTs. Okay, so we had the instates. They are created by acting with creation operation. Okay, and the important thing here to notice that this both the creation and annihilation operators. They are non-local operators. Why are they non-local? Because they create and destroy. You're not too pissed about that. Okay, they are non-local because they create or annihilate states of definite momenta. Okay, so if they have definite momenta, they cannot have a definite position. Okay, just a sensitive principle.
Yeah, actually, these vectors are not even the Hilbert space.
Yeah. So they are non-local in this sense. The fields itself, they are local because they are just a Fourier transform. Okay, you just write the scalar field is just a Fourier transform. Okay, then we have those exponentials here with the gradient operator plus the conjugate exponential here with
over the mass shell.
And okay. And other some normalization factors. Okay, so the creation and annihilation operators that you use to create states are non-local. The fields itself that you're working in your quantum field theory are local. Okay, and the interactions are local and so on. At least you choose them to be local. And okay, that's what happens in usual quantum field theory. Okay, that is usually it is not highlighted because you're not supposed to run CFT together with quantum field theory. But on CFT, it's just okay. Okay, so the conclusion is, okay, the punchline, if you want, is a non-local operator. Gives rise to your states. It's just ordinary quantum field theory. Okay. What do we do for CFT? Okay, these are CFTs now. Okay, you can since I highlighted the non-local, of course the result will be a local operator. But why is that? We saw here that we have this natural set of primary fields. Again, on primary operators and using them interchangeably. And if I take the vacuum, the conformal vacuum, okay, and I act with primary operator, okay, it's located at the origin, so it will be a primary because it naturally solves this equation. And this delta is just means that it has scaling dimension delta, okay? This would be an eigenstate that are called delta in brackets, and if I measure this guy here, I find it to be an eigenstate of the scaling operator with this eigenvalue. Okay, how do you compute this? You write this like this, and then you use these commutation relations. Okay, and you find that it is indeed an eigenstate. Okay, but here's the point. Okay, so this will be a primary. I'm just not write this right now. Let's go with it. This guy is a local operator. Why? It is a local operator because it's located at the origin. Okay. It's just as simple as that. It is located at the origin, so it's a local operator. Okay. So on CFTs we have local operator. Creates states. We can naturally ask what happens if I put it on pictures. Okay, remember we're doing radial quantization. Okay, so we fixed an origin. Okay, so I'm setting this guy here. Okay, and then if you want, you do the path integral, and you end up with a state, okay, in a given sphere or radius r, okay. So what happens if I insert an operator here, away from the origin, okay? So what we do is just translate the origin. The convention was that. Okay. So we insert this operator at x now. Okay. Acting on the value. All right. I will rewrite this operator as okay. This is just the way to translate operators. Okay. And of course, this is the vacuum. It is invariant under any conformal symmetry. Translation is a conformal symmetry. So this guy here just vanishes, and from this guy here, just will. I said it does not match. Okay. You get the zero eigenvalue here, so the exponential vanishes. Okay. That's what I meant. You should correct me. Okay. Sometimes I just get carried away and I say these things. Okay. Sometimes I notice them, sometimes I don't. Okay, just me or it's getting hard?
That one was making some weird noises.
That one was making weird. It looks like he went to ventilation.
Maybe.
No. Okay, so get back here, okay? So we have this. Okay. This is by definition just this state, okay? And then what do we do with this exponential? We can just expand it, okay? This the identity plus I x2 plus blah blah blah. Okay, so I'll call this state say state x. This state is a linear combination of a primary, okay, and then a bunch of descendants, okay, because I'm hitting it with the translation operator, okay. So this state here that I call the chi, if I act with the special column generator on it, it won't be 0, okay. Then because I know there will be some descendants in this linear combination, okay. So this state is not a primary. So if it's not a primary, it must be a descendant. Okay. So this will be a descendant. So by acting with and again, this is a local operator. Okay, it's a local operator located at point x. Okay. So what is the lesson here? With local operators on a CFT, I can create all the states of the theory. Okay. What are all the states of a CFT? They are primary states and they are descendant states. That's just a way to create it. Okay. So again, in the standard quantum field theory, I create states of definite momentum with the creation and annihilation operation. So what it means is we have, say, a mapping, if you want, from non-local operators to states, Hilbert space states. In a CFT, we have a mapping from local operators to the Hilbert space states. Okay, we know we can go. Okay, even a local operator, we can build a state. Okay, so this is starting to look something like this. Okay, now what we must check is if we can go back. Okay, given a state, can we find a unique operator, local operator? Okay, CFTs, of course, can have non-local operators as well. Okay. The story is just that for local operators, we have. So maybe I should call this local operator state correspondence. Okay. CFT. But people usually just they don't talk about the local. Okay. So, are there any questions about that? Is this up? Oh, I want to. I guess no problem. So we just discussed how our operators, or local operators, have states. I want to see the other way, okay? And it is easier than my what appeared at first glance. And of course, this is just auto formal. Okay, just a priori, you can do this. Okay, we will see examples later. Okay, and that is the reason why the other way is easy, because just an in-principle discussion. Okay? We're not worried about how we actually do it in practice, even in theory. But okay, the point is, what do we have? How do we determine an operator in a field theory? One way to determine an operator is to determine all of its correlation functions with every other operator on the theory. Okay? If I know all the correlation functions, I know all the physical information regarding that operator, so I can say I determine the operator. Okay? And what is a correlation function? We usually write a bunch of fields and operators here. What this practice means is just a shorthand, usually. Okay? From vacuum to vacuum states. Okay? And so, what about it? Okay, so let's consider something like this. Okay? Have some fields here. And instead of the vacuum, I have a state delta. Okay? I want to compute that correlation function. Okay? But what is delta? This is just this. Okay? So, can we rewrite this like this? Okay? And I can do this with any operators phi here. Spinless, spinful operators, any number of them in here. Okay? So, that's basically it. From a state, I choose a state. This state can be created by an operator located at the origin with the same scaling dimension. And from this, I can do this game for any correlation function between, say, the vacuum and that state. I rate that state by using that result, that definition. If I do this for every correlation function, then I have a map from states to local operators. Okay. Let me just see. I know you're not happy about it. I guess that's the end of it.
Sorry, I just didn't get it. Sorry, you just repeated. I just didn't understand.
No.
So what exactly do you want to show?
Okay. Okay. I want to show this. Okay. The correspondence, the word correspondence means there is a map.
And
okay.
by operating, you mean what now? You mean the one at the origin, or no? Okay.
If it's not at the origin, I can just play this game. Okay.
No, sorry. Say again. What do you want to show?
I want to prove the operator state correspondence. Okay. What is the operator state correspondence? It's basically, if you want, is like an isomorphism between the space of local operators in a CFT and the space of Hilbert space states. Okay.
Okay.
Can go from one to the other. Okay.
Yeah.
Even local operators you can find
Yes.
the states, and even the states can find
Yes.
the local operator.
Yes.
Okay. This okay. Let's call this from. Okay, let's call this say A. This is what is written there. Okay, this is the operator to state. Okay. This is what is discussed here. Okay, I defined. Okay, I have a vacuum. Okay, the vacuum is me.
And then you can define the state by. Okay.
I define like this. Apply those. If you want, you can apply the instrumentation later. I just erased here to check. Okay, this will be indeed an eigenstate with this eigenvalue. Okay, and if I insert it is local because I put it at the origin. But if I put anywhere else, okay, it's still local. Okay, just put outside of the origin.
This is already something specific because this is like any local operator becomes a primary field. A state which that's like a specific state, which is an eigenstate of.
Okay. I did this for one eigenstate, okay, if you want, but then I can, if I want to look at another eigenstate with the eigenvalue delta 2, then I can use another local operator that has O delta 2.
Okay, so you say that the deltas form a basis of the Hilbert space, and I can generate any state in this Hilbert space by any linear combination of these O deltas.
Yeah.
So that shows me that I can reach the entire Hilbert space.
Just one thing. This is the physicist proof. Okay.
Yeah.
Okay. If you want to go for a mathematical proof, then it'll be much more involved.
I just want to understand what is going on.
Okay. I just thought I should maybe clear that up. Maybe it helps. Okay.
No,
and I'm not giving the most vigorous proofs here.
I just want to understand. Okay, you say, okay.
But you got it. That's it.
Okay, I can generate any state in the Hilbert space by linear combination of these. Okay.
Okay, this is the okay, given operator can find a state. Given operator can find a state.
So now why did you what was this again about the local the operators
away from the origin?
Yeah, so why did you do this?
Okay, because it's just to show that if I put them outside the origin, I'll end up with just a catch. Okay, I insert an operator at the origin. What if I insert it outside the origin? Okay, I can show it to them. What happens? I get a linear combination of eigenstates. Okay, and this is a descendant state. Okay, why? Because this operator at point x.
This I understood. I just want to see, but in the first line I already showed like I can reach the entire Hilbert space because the Hilbert space is spanned by linear combination of these deltas.
Yeah.
So this is just an observation.
Yeah.
Which I don't. Okay.
Because it is an important observation. It has its uses, but
okay, no.
Okay, but you could stop here.
Okay.
They just go okay, then apply linear combination and so on and so on. Okay.
Yeah. And in a way, just like any descendant state, of course,
what happens is that, okay, for some reason, I don't know what went through my head, I wrote it, then I erased, these are the primaries.
These are the primaries, yes.
Because this operates looking at the orange, so it can be there. So when they give you an X on it, it will give 0. Okay,
yes.
So this state here will be a primary.
So
be a primary because
that's like the first thing where I already get confused, because now if all the deltas spend the entire Hilbert space, this means I can spend any state as a linear combination of primaries.
No, okay, this is the point, okay? This generates primaries.
Yes, but
this generates descendants. Descendants plus primaries equals the whole Hilbert space.
But the thing that I didn't get is like, you're saying that the deltas spend the entire Hilbert space. The states delta are a complete basis of my Hilbert space. Well, I asked you like a couple of minutes ago.
Okay,
probably they shouldn't be a basis, right? Since
vigorously. This generates primaries. This operator at the origin primaries. Okay?
Yes.
Operators outside the origin, descendants.
Okay, so,
Okay. Primaries plus descendants equals the whole Hilbert space. Why? How do we know this? Because of the ladder structure, okay? Of the conformal algebra.
yes. Okay,
The
so,
point is that the primaries are more important because from them I can construct everything else.
yeah, just try to, so it's not, it's just about, because I want to get the picture, like before we talked about the shells, like we said like Q of t, you have like your momentum eigenstates which form a complete basis, and then you have the Hamilton operator which makes you like a translation from one timesheet to the other. So here you have now the shells, and on each shell you have a Hilbert space which is a linear combination which is spanned by these deltas. But then to reach the entire Hilbert space of everything, I have to make my translations from one shell to the other, which is done.
Well, what takes you from one shell to the other is the dilatations, not the translations.
Exactly, is the, and this, so I just want to like get this analogy. In Q of t, I have my entire Hilbert space spanned by the eigenstates of the momentum operator. And I make the translations in time, which gives me the same Hilbert space, also spanned by the momentum. So here now I have like my shells of the sphere, who have a Hilbert space that is spanned by all primary fields. That's
No, you have descendants, that's it. Okay, if you take this shell here, okay, what I've shown you is that, okay, if I insert an operator here on this Hilbert space,
yes.
that's located on the shell. This operator, oh, okay, what is this operator, okay? This is the same operator that I inserted here. The lesson is, if I insert it at the origin, it will generate primaries. If I insert the same operator, but outside the origin, say on this Hilbert space, on this shell, then it will generate descendants, okay? But I could just as well take, say, another operator, another eigenvalue, put it here, and generate primaries, because I will just, have to solve the differential equation to find what are the operators that are still primaries outside the origin, okay?
I'm just confused by, okay, it's like very confused, sorry for, but
It
like,
takes some use to.
like if you make this analogy between Q of t and C of t, I have like the same Hilbert space on every time slice, which are the eigenstates of the momentum operator, and that's a complete set. So here is something else going on which I don't understand. That's my confusion, because before you said like in this analogy, we have the eigenstates of P operator, Q of t, we have now the eigenstates of D, and I should think this like being the same, but if I would take this literally, I would say, well, my deltas form a complete set, and I can make the translation from one shell to another by now my new time evolution operator, like, but the Hilbert states would be the same. But something I got wrong in this picture, and you're trying to explain, but I still didn't get it, which is like where are descendants in this picture, like where?
What are descendants?
The descent, because the deltas are the primary fields, no? Like
The delta is just the.
So I think the question is, does the deltas span the entire Hilbert space, this delta basis?
it doesn't
Okay,
look like
what-
it, no?
what-
Yeah.
Is
What
it
delta
the
are we talking
basis?
about? We are talking about
Yeah.
these deltas.
Yes.
Yeah, these deltas.
Okay.
Are these the basis? Because if they are,
Okay.
then every
Then
state
should-
should be a
Okay,
basis.
okay.
Spend this
Say,
primary.
I have a state here. Say I have this primary. Okay.
Yes.
For example. I could have another eigenstate with this eigenvalue,
Yes.
right? This will be a descendant. Most likely, at least most likely be a descendant, because I just, it's exactly plus one, so I act with a moment operator. So it is an eigenstate, but it's a descendant, it's not a primary, okay? Because it's built from primaries. I don't know if that.
Yes. Okay. So that
Helps.
I guess, I think that helps.
I mean, you could maybe you could have a primary with exactly 1 unit above.
No, so the allowed deltas.
But
So the primary states are just the eigenstates of the spectrum.
So, just try to think about the
Okay.
harmonic oscillator.
Yeah, I'm confused by that also.
It's
Yeah.
because